All right, welcome. In this video, we're going to take a little sidestep. We've been talking about algorithms and algorithm analysis for the last couple of videos. And I want to continue doing that with a little bit more detail. And so to do that, I need to introduce a few extra concepts, a few extra details. So we've been using a kind of logic thus far that we've been calling propositional logic, which is sometimes also called first order logic. And I want to add to that now, or expand to that, by including something we call logical quantifiers, which is, again, something that sort of grows on or builds on top of the logical structure, the propositional logic that we've already been looking at. So to do this, we're going to expand into a realm of logic that we call predicate logic. And part of the reason is because we're going to introduce part of speech, which is the predicate. And so we've probably already studied parts of speech where we know the difference between the subject and the predicate of a sentence. Well, we're going to bring that into the understanding of the subject and the predicate now of a assertion, a proposition. So again, up until now, we've been treating our propositions as atoms in the sort of Greek meaning of that word, meaning it indivisible or unbreakable. So we would just give a proposition a name like P or Q or R. But now what we're going to do is we're going to split that proposition into its pieces. So it's no longer going to be an atom. It's now going to have components. And we're going to split it into the subject and the predicate. So here I've got a simple example. Up until now, we might have used the label P for the proposition snow is white. Well, now what we can do is we can split that into two sort of components. The subject of this sentence is snow, and so we might give it a variable name now, like A. You'll notice just conventionally, while we're still using lowercase letters here, I've switched from P to A, and again, this is just a convention. P, Q, R, P is for proposition. That means more of treating it as an atom. When we step away and we start treating it as a variable, we might leave it as an X, or if it's some variable that's been assigned some value, like in this case we're going to assign A to be the value snow, then we might use letters like A, B, or C instead of X, Y, and Z, which we usually reserve for variables that have not been assigned a value. So if we're going to assign A to be the value snow, then we're going to have this other, it looks like a function now, but we'll call this predicate. And I'm going to use the capital letters for predicates here. And I've chosen to, if I didn't know what my predicate was, I might use capital P for predicate. But in this case, my predicate is going to stand in for the phrase is white. So again, a predicate in as a part of speech is a sort of a verb phrase, which means if you're looking in your proposition for it, go find the verb. In this verb, it's is. But usually a verb it's not just the verb by itself. Sometimes it is, occasionally it is. But often it's a verb with other components, maybe an object or other stuff as well. Well, we're going to sort of draw a circle around that whole thing and call it the predicate. Okay, so the predicate is that whole verb phrase. In this case, is white. Okay, and here we've also usually the predicate, because it's only got that verb phrase, it's usually got this open part, this part that needs to still be filled in, which is the subject. What is white is the question that is asked if we only have the predicate is white. And so we sometimes might phrase that as X is white here, where X is that variable. Okay, so we might write it as W of X, which is the notation, but it really is standing in for something like this: X is white. And of course, there's lots of different predicates that we could imagine. Is white is one, is green for grass is green is another example. We could have a different predicate for that, is tall, is long, and then we can have other kinds of predicates that maybe take more than one argument as well. Is taller than is a predicate that takes two variables. X is taller than Y. Depending on how you assign the X and the Y, it could be true or false. Likewise here for our snow is white, how we assign our X here could make this true or false. Snow is white, so if we assign snow in there, we assume that will be true. So here I've got the proposition P, where we've plugged in A for snow into the predicate is white. We now get snow is white, the proposition that we have been discussing, and that one is true. Of course, if we took grass instead, maybe B is equal to grass, and we plug that in there, grass is white. Again, presumably that would be a false proposition. Okay, so again, all we're really doing here, something we're probably already familiar with in studying language and English or some other language classes. Now we're going to take that and apply that in logic, break our proposition into its components, its subject, and its predicate. And again, for very simple propositions like this, it's usually quite easy to do that. Okay, so I think I mentioned the B is grass bit. And maybe the third example I've got here is, well, it makes sense that we should assign our variables to be something that has a color, but it's possible that we could also assign something that doesn't have a color. So the number 5 does not have a color associated with it. So we usually would say in this case that that's still false, because the predicate or the verb phrase does not apply in this case. And usually we sort of say by default then, if it does not apply to that type of object, then we'll just say it's false. And that kind of makes sense. I'd say that kind of makes sense, and it's sort of our default way to talk about it. But again, if you want to get into sort of into the weeds of philosophy, you can probably find a philosopher who will argue with you about this, about whether 5 is white is true or false. There might be some out there that say it's neither true nor false because 5 is not the type of thing that has colors. Well, that's left as a sort of an erudite philosophical conversation that we'll just push to the side, where for most purposes, most of the time when we're working, yeah, 5 is not white, and we're all sort of comfortable assuming that that's the case. Okay, so again, it's a weird case, but let's push it to the side for now. Okay, so the idea of the predicate allows us to start to make different kinds of logical sentences, and these are logical sentences that are a little bit harder to work with just propositional logic. And the sentence that we might want to consider is a sentence that applies universally. Now, universally, that when we say something applies universally, we mean it applies to everything, or it applies to maybe everything in a category. So maybe all the numbers or something like that. And so often when we are talking, in general, when we're talking about math or other things, when we say we're talking generally, what we mean is we might say we're talking universally, meaning it applies to everything. The generally that we're talking about means it applies to everything. So what we can do now, rather, when we have this predicate introduced, is we can now introduce what we'll call a quantifier. Now, quantify means to give a number to count, if you will. So a quantifier is something that will apply numerosity or a number to something. To what? To a predicate. Well, that's what we have. So remember, our predicate, we might say, is unbound by itself. When we say x is white or x is green or whatever our predicate is, the x, the variable, is unbound. And one way to bind it is to just pick an object and stick it in there like we did. Snow is white, grass is white. Those are different objects. But another way we could do that is we could add a quantifier to it. And the quantifier is just going to say something about the number of objects that have that predicate. So how many things are white? So the simplest one, the universal quantifier, the everything quantifier, says everything is white. If we apply the universal quantifier to the predicate is white, we're saying all things are white. So let's take a closer look at this quantifier. This, again, I'm calling this the universal quantifier. It applies to everything. And it has this strange symbol, it's the upside down A. Okay. Why A? A is for all, so sometimes the universal quantifier is sort of shorthanded for all. We mean for all numbers, something, something, something. And so the upside down A is taken from the word all. Okay, now why they flipped it upside down, I don't know. Some logical folk over 100 years ago we're deciding what notation to use, and this is the one they picked, and it's the one we're stuck with, so we're sticking with it. Upside down A's. So the upside down A, and then this X, what's the little X there? That's telling us the variable that we are binding with this quantifier. So again, remember, the predicate is unbound by itself. One way to bind it is to put an object in there. Another way to bind it is to apply a quantifier to it. So this is saying for all the x's. Okay, so maybe we're going to say for all the x's p of x, and so that's what it means when we apply this predicate or apply this quantifier to this predicate. Then that just means p of x for all subjects x, whatever subject x we might pick. Now, remember, when we were talking about set theory, we sometimes restrict our universe to numbers or mammals or something like that. And so we may restrict that in our universe to something like that. But if we don't restrict the universe, then we really just mean all of the things, no matter what they are. So it's rare that all of the things are going to have some proposition that's true of them. It's hard to find a property that is true of every single thing you can imagine. Now, a lot of the propositions that we've been working with so far actually have been propositions that have used a universal quantifier in them, and up until now I'm going to say I've smuggled it in, I've snuck it in. It has been there, it's just been invisible, and we have been kind of ignoring it, and that's because it's very natural in natural human language and also in natural human logic to assume that when someone makes a claim, they mean it generally. They mean it's a general claim. Specifically, we're working in a mathematical context or a computer science context. If someone says, all even numbers are divisible by 2, okay, I've said the word all in there, so I've smuggled it in, but let's change it a little bit. If someone says even numbers are divisible by 2, your brain doesn't assume they mean, oh, there's some even number divisible by 2 and some are not. We immediately leap to the assumption that what you're trying to say is all the even numbers are divisible by 2. And that makes sense. And so since our brain automatically fills that in, what that means is a lot of the time we don't actually use the quantifier when we don't need to, when it's assumed. And that just simplifies things. Okay, but we're going to step into a realm where maybe leaving it out is going to confuse us more than it is going to simplify things, so we're going to want to bring it in, and so that's why we're going to introduce it now. Okay, so that's the universal quantifier. Let's take a look at, again, some more examples. So here, we did the one with snow is white, but let's look at this one. O of x, let's say O of x is the predicate, is an odd integer. Okay, now, we could come up with one statement, which is just for all x, O of x. For all x, O of x. Okay, if we had that argument, what that would be saying is for all things x, those things are odd integers. That means 1 is an odd integer, that means 2 is an odd integer, that means 3.5 is an odd integer, that means I am an odd integer, that means you are an odd integer, that means everything is an odd integer. Well, that's obviously not true. Obviously, we have lots of examples in that list I just came up with that were not odd integers. So obviously that statement would be false. Okay, but another way that we can use the universal quantifier, and any other quantifier for that matter, is here where I've got it stated for all x. I'm going to change how I state it here. Notice here I say for all n in z. Remember, z is the integer, so that's saying for all n's that are integers. So what that does is, that's a little bit of a shorthand ahead of time saying restrict what we're talking about, not all of the things, but just the integers. Okay, restrict to the integers. But now that we have an integer, all of the integers n, now what does this sentence say? Let's see if we can read what this sentence says. This says, now remember this biconditional here, that's an if and only if. That's saying n is odd, right? Okay, n is an integer is what we're told by the quantifier. It's saying n is odd if and only if n squared is odd. Okay, that's what I've got here as well. n is odd if and only if n squared is odd. That's the sort of the codification, if you will, of this more natural language sentence using the predicate O of x is an odd integer and this universal quantifier. It's saying for all of the integers, if the integer is odd, then if you square it, it's also odd. Is that true? Or is it false? Well, we might want to rush back to our notes or go revisit one of those earlier videos, but we did actually prove this statement, or at least a close statement, one down here below, related to this, which is that, yes, indeed, if you remember, if you multiply two odd numbers together, you get another odd number. So odd times odd should give you odd. So this is indeed a true statement. And I've got that sentence, that closure of odd numbers. What I just reiterated when I said take an odd, multiply it by an odd, you'll get another odd. We called that the closure of odd numbers under multiplication when we looked at that earlier, this closure idea. And so again, I can express that mathematically this way by saying pick any, for any n that's an integer, and for any m that's an integer. These could be different the way we've set this up. Now we've got a same sort of statement here. It's saying if the two integers we've selected, n and m, are both odd, n is odd and o is odd, then n times m is odd. And that's the idea behind the closure of odd numbers under multiplication. And in fact, since the even numbers are also closed under multiplication, this could be replaced with an if and only if as well. Okay. The only way to get an odd number is by actually no. Okay, so let's be careful there. I said because of the closure of evens, that's leaving out a case, and I don't want to be misleading us here. What would we need to have for the biconditional? Let's just, first of all, what would it mean if we turn this arrow around, or if we put two heads on the arrow like we did here? What's the backwards arrow mean? It's saying if the product is odd, if you multiplied two numbers together, n and m are odd, then n and m must both be odd. Now, is that true? I'm going to leave that one as maybe a little exercise or something for you to think about. What this is saying, so let's see if we can get this exactly straight again. What this sentence says right here is, if you have two integers, and they're both odd, then if you multiply them together, you get an odd number. Now the backwards version said, say you have a product, someone else multiplied two numbers together and gave it to you. The number they gave you is odd though. They didn't tell you what the two numbers were. Can you be confident that they're both odd? If you think the answer is yes, then the backwards arrow is also true. If you think the answer is no, then the backwards arrow is not true. Okay, I'm going to leave that for you to consider. Okay. Here I've got a last example. This is just an example I remember from my college days, which are now 2 decades behind me. But in my college days, this common sentence was used to explain quantifiers. Every bachelor is unmarried. Even then, 2 decades ago, I thought this was kind of a weird expression. The word bachelor is kind of an archaic word. Of course, then about 2 decades ago, they invented that TV show called The Bachelor, and so it came right back, and everyone starts to understand what a bachelor is. So what is a bachelor or a bachelorette? At least according to the TV show, a bachelor is an unmarried man, and a bachelorette is an unmarried woman. Again, maybe it's a strange archaic term. So here I've more focused on the unmarried part. That's the part that makes you a bachelor. So here the sentence, every bachelor is unmarried, we could codify that with just a simple proposition P if we wanted, but then how that proposition interacts with other propositions is not clear unless we break it into its quantifier components. So what do I mean by that? So say someone told us this is true, that this statement is true. Every bachelor is unmarried. This is a definition, so usually we take those without question. We don't need a proof. And then someone else told us that their friend, Bob, was unmarried. Then we should be able to conclude from that that Bob is a bachelor. If we could conclude that, then that's not clear from the propositional logic, because propositional logic doesn't have any rules for words like every. And so that's why we had to introduce the universal quantifier here, is it's going to give us a tool to handle phrases with the every word in there, or all, or any other words that mean roughly the same thing. So here, to take this proposition, every bachelor is unmarried, we're going to translate that using predicate logic, using, now up here I've only used one predicate, but down here I'm going to use two. One is for bachelor, and one is for, I'm going to scratch out the un there and make it for married, okay, is married. So I'm going to have two predicates. B of x means is a bachelor, m of x means is married. Then I can recast this by saying, for all of the things, now here I'm not saying what thing. I could say for all people, but maybe you want to say your pet dog's a bachelor, that's fine. So I don't want to restrict that. I'm saying for all the things, if it is a bachelor, the if comes from this arrow, right? If it is a bachelor, then not, this is a negate, then it is not married. Okay, and we can see that that makes sense then. For all things, if it is a bachelor, then it is not married. That's capturing what we're trying to say here, that every bachelor is unmarried. Now again, I mentioned this is a definition, and usually definitions are if and only if, so we might throw it backwards. Although again, I've left out part of this definition, which is the male part, the gendered part, which again, that's sort of irrelevant for this discussion. So we'll again brush that under the rug. But this was just again another example. We've got maybe 2 or 3 now examples of how we can use that universal quantifier with a predicate. So let's look at another quantifier. Now these aren't really the only 2, but these are the 2 most common ones, or the 2 that show up a lot in logic. And one reason for that is they're also sort of, I was going to say opposites of each other. That's not exactly right. We'll see why in a second. But they're definitely, I want to say, 2 sides of the same coin. Okay. So the universal quantifier said for all of the things the predicate holds. The existential quantifier, existential means exists, something that exists. So we sometimes rephrase it when we say this as, there exists something. And again, that phraseology, the there exists, is a very logic ease type phraseology, in the sense that we usually express that there exists, we express sentences in that way when we want to emphasize a couple things. One, that something exists, but also maybe that we're not really sure what it is that exists, other than that we know it exists. So for instance, we might know that there exists a prime number. Okay, prime numbers are notoriously a little bit hard to know, but let's say we probably we might want to say something. I know that there exists a prime number greater than 10 billion. I know there is because there's certain proofs that have proved to me that there is, but I might not know one. I don't know any off the top of my head, any prime numbers greater than 10 billion. I just know that there is one that exists, which means if you don't believe me, 1, I can either try and prove it to you, or 2, I can jump over on Wolfram Alpha and ask them. Wolfram Alpha is a very powerful mathematical computer, and it has enough computational power to tell me a prime number greater than 10 billion. It might even be able to tell me a prime number much greater than that. But for example, here's another example. currently, right now, in humankind and human history, there is some largest prime number that we know of. I don't know what it is. It's probably really big. But whatever that prime number is, the largest one that all human mathematicians know of up for all history till today, whatever it is, I know there's a bigger one. So even though no one's ever found a bigger one, I know there's a bigger one. And even though I'm recording this video here September 5th, 2020, you might be listening to this video somewhere in the future, meaning that larger prime number may have already been discovered. Well, there's a bigger one than that too. So that's the kind of statement that we can express using the existential quantifier, the existential quantifier that expresses that something exists. Okay, and we could imagine it could be used for other, maybe more philosophical discussions, that certain types of principles or properties exist, that maybe God exists or something like that. All of these things might be something that is expressed in this way, but more commonly we use this quantifier to express existence of things in very formal and mathematical contexts, like computer sciences, which I assume we're going to use it in shortly. So again, that's what the existential quantifier is. Very similar to the universal. We have a symbol for it. We can't use the upside down E, and that's because the upside down E is also E. You flip it up, it's fine. So we use the backwards E, and then think about it, the A is the same thing. We can't flip it backwards, it's the same, so we flip it upside down. Whatever it is, we flip the E, so we read it, so it reads a little weird. It's the backwards E, but again, where did we get E from? From exists, the word exists. So it's usually pretty easy to remember. For all and there exists. So there exists an X, same thing as before. There exists an X. If we don't tell you what the X is, we mean any old thing. There exists something, X, such that P of X is true. So again, we've got some proposition. Let's start with is white again, okay? For all of X, X is white, that's saying everything's white. That's not true. That's certainly not true. Even all the colored things are not white. So there are some things that are not colored at all. So that's not true. But then if we flip it from for all to a there exists something that is white? Oh, sure, that's true. I mean, there's lots of things that are white. I've got a piece of paper right here that's white. Snow, we were talking about snow, that's white. There's lots of things that are white. So to prove that something exists that has a particular property is actually usually pretty easy, because you just have to find one that exists. So an example, there exists an odd number. Is that hard to prove? No, 3. There you go. There's an odd number. There exists one. There's one. And that's all we need to do. Okay. There exists, sometimes we have to do a counterexample of some kind, which means trying to find something that exists that violates some property. So we were talking about closure of odd numbers under multiplication, which happens to be true. Okay. And we were thinking about if you have an odd product, did you have to have 2 odd multipliers, factors? And the answer actually is yes. But if you have an even product, so you have a product n times m, is it true that both n and m were even? The answer is no, and here I can prove it true. 2 times 3 is 6. 6 is even. But 2 is even and 3 is odd. The only thing you need to get a even product, n times m, that is even, one of your 2 factors has to be even. Not both of them, only one. And we can prove that, as I just mentioned, with that counterexample. 2 times 3 is a good example. So existential quantifiers are used. Sometimes they're easy to prove because we just need to find some example. And usually that means pick your favorite one. That works. Not all of them will work, but pick your favorite one that works. Okay, so I guess I've got an example here. Again, still using that predicate is an odd integer that we had before. I've also introduced is an even integer here, so we can use them both. So here I've got a proposition. Well, maybe instead of reading the English version first, let's take a look at the codified version and see if we can understand what it means. So again, this bit here says there exists. There exists what? An integer n. So again, hopefully we're getting comfortable sort of reading that notation. That means n is an element of the integers. So there exists some integer. Okay, there's some integer such that what? Whatever's going on inside our brackets here. There exists an integer such that n is even and n is odd. So that's saying, this is saying that there is some integer that is both even and odd. And at least according to my slide here, that's false. That makes sense. There's no integer that is even and odd. And you know, the only integer that comes to mind that might be a good candidate would be 0, because it's not positive nor negative. Sometimes we lump it with the positives. But of course we know 0 is defined to be even, so it's an even number, not an odd number. It's not odd, it's even. And in fact, even and odd are known to partition the integers, so it's impossible to find such an integer. Okay, it says, what does this mean? So again, there exists an integer n such that n plus 4 equals 0. So there exists some n that this is true. Is this true? Yes, there is some integer n such that n plus 4 equals 0. How do we prove this true? Well, we need to find that integer. Which integer is it? So this is an example sometimes. So I mentioned earlier that proving an existence proof is sometimes quite easy because you just pick your favorite example. Well, when does proving an existence proof become hard? Is when we have the problem of what I'll call the needle in the haystack problem, where we have something we're looking for. There is an integer that exists that has this property, but maybe there's only one integer that has this property out of all of the integers, and of course there's infinite integers, so finding that integer is sometimes a challenge. Well, in this case, it's not that hard. If you've got a little algebra behind you, we know it's minus 4. Of course, minus 4 plus 4 equals 0. And so this idea shows up a lot in algebra. The whole purpose in algebra of doing some algebraic manipulations of the left-hand side and the right-hand side is to find out which n it is that has this property, or x if we're solving for x, and so on. And so again, even though we haven't been using existential quantifiers up until now, they've been showing up in our math and logic throughout up until now, and we've just been leaving them on the side because our brain has been plugging them in and using them. It's just we haven't made them explicit yet, and that's the goal here, make them explicit. Okay, what about this one? Can we express this proposition? There is no largest integer. Okay, there's no largest integer. So, okay, I got a hint here. What does my hint say? What does it mean to be the largest integer? Okay, that might help us. So what is the largest integer? So, if you're the largest integer, then you must be greater than all. So I'm trying to pull out the pieces. So one of the pieces is greater than all. The all there, that part there, the all is hopefully making us think there's a universal quantifier showing up here. Okay, the largest integer must be here. Let's try and do this together. The largest integer must be greater. So somewhere in here we're going to have the greater sign, and somewhere in here we're going to need. So something's greater. We said there's a for all here for all the other numbers. Okay, so let's maybe say this for all the integers. For all the integers n, let's say we have some integer, I don't know, m, that's the largest. Okay, then our m should be larger than all of the n's, right? For all of the integers n, if m is our largest integer, m has to be larger. I'm going to put the equal in there because m is an integer too. So m needs to be greater than all the other integers, but it needs to be equal to itself. Okay, now the problem with this sentence that I've got written right here is the m is unbound. Okay, it's a variable that's unbound, and when you have an unbound variable in a sentence, then your sentence is not a proposition. It doesn't have a meaning. Or it might have a meaning, but it doesn't have a truth value yet. It won't have a truth value until you bind that variable. So one way we could bind that variable is we can plug it in. So say we knew what the largest integer was. Let's say it's 1,000,000. Then we could plug in 1,000,000 there, and then this should be true. Okay, but of course this is not true. 1,000,000 is not bigger than all of the integers because there is no number that is bigger than all the integers. But we're not saying that 1,000,000 is bigger. We're just saying there exists some integer. There exists. So sometimes there exists, we like to stress the word some, because some comes with a couple of connotations that are helpful here. Some means at least one. That's the important numericity part here. At least one, not 0, at least one. But the other thing about some, the word some, at least in natural language usage, is it conveys sometimes that we don't know which one, right? There exists some integer m, I don't know which one, but there exists some such that it is greater than or equal to all the integers n. Now again, this is a false statement. Of course, there's no greatest integer, so this is false. But the purpose of this enterprise was to say, could we translate that into a logical sentence that expressed that meaning, and then use that maybe in our reasoning. So here I've actually, looks like I've got this one a little bit differently, because this is why, this is my own misreading. The sentence that I just wrote on our previous slide was the sentence, there is a largest integer, not there is no largest integer. So of course the one that I wrote there, I said was false. There is a largest integer. There is, that one would be false. Well, all I did here to make it there is no largest integer is that we just stuck the negation sign out front. It is not the case that there exists an integer such that for all the other integers n is greater than or equal to m. Now, did you hear what I just did there? I just took this and read it in what I call logic ease. In logic ease, you're sort of reading the symbols out, but it makes a kind of weird sentence that doesn't really sound like what you mean. The natural language version of this sentence is, there's no largest integer. But the logic ease version, let me read it out one more time, is, it is not the case. So when the not comes first, we usually say, it is not the case that, and the word that means that whatever's coming next is a proposition. So the word that in this sentence is really filling in for these brackets. It's when we say, it is not the case that the bracket opens now, okay? So now the bracket opens. It is not the case that there exists an integer n. So I just read this sign out directly. There exists an integer n. When another quantifier comes in, we will usually insert another that, but we stick the such in there in front. So here we go. Follow me through again. It is not the case that there exists an integer n such that, now we've put the such that in, such that for all integers m, and now we might put another such that in there, although it's starting to get wordy, right? So sometimes we'll delete that out and we'll just say n is greater than or equal to m. So let's go through and read the logic ease version of this all the way through one last time. It is not the case that there exists an integer n such that for all integers m, n is greater than or equal to m. Okay, let's see if we can pull out the logic keys a little bit. It is not the case that there is some integer n that is greater than all the integers m. So to take out a little bit of the logic keys there, I've put this for all at the end in our natural language expression. And that's something that we commonly do when we have multiple quantifiers like this, is that to place it into English, instead of saying there exists something such that, therefore all something such that there exists something such that, and having this long chain of such that's, we'll often redistribute those phrases throughout the natural language later on so that it flows a little better. But again, our exercise here is to try and figure out the formal structure of that sentence so that we can work with it. Now the thing I want to do now is sometimes when the knot's on the outside there, we want to move the knot on the inside. Like the way we've expressed this, there is no largest integer is right in the middle somewhere. It is not the case that there is a largest integer. That's a more awkward logic ease version way of saying it. So what that means is that to translate that a little bit more, I want to talk about negating quantifiers and what happens when we negate them. So let's just think a little bit about these propositions, if you will. It is not the case that all x's are p. It is not the case that all x's are p. Or this one, it is not the case that there exists an x that is p. So what about this first one? It's not the case that all x's are p. Well, I think what that is saying is that there's at least some x that is not p, right? If it is not the case that all the x's are p, if all the x's were p, then all the x's are p. That means none of them are not p. But if at least one of them is not p, then that means not all of them are p. So what the interesting thing we see here is that we can actually bring the negation through the quantifier, but only if we flip the quantifier. And that's true for the existential as well. Let's see if we can reason that through. It is not the case that something is p. So it's not the case that something is p. Another way of saying that is all things are not p then. So that's just the definition here. Here, these are definitions, if you will, but we just sort of reasoned it through in our own, we plugged it into our internal logical computers and hopefully it came out feeling correct, okay? So again, taking a quick look at these, the rule that I usually like to remember is if I want to bring the negation inside, it actually flips the for all to an exists. Okay. And so let's try and apply that to our sentence that we had here. There is no largest integer. So if we bring this first one in, I'm just going to bring it in one layer first, and that's going to flip the for all. Okay. So now let's see what this is saying. All integers are such that it is not the case that they are bigger than all the integers. So this one is saying it's still logically equivalent, but it's saying something different. This one was saying it is not the case that there is a largest integer. This one is saying all integers are not the largest integer. So let's go through that one more time. The first one's saying it is not the case that there is a largest integer. Okay, that's what we're trying to say. But the next one is saying all integers are not the largest integer. So that's really logically equivalent. That's trying to say the same thing. If you're trying to say that there is no largest integer, but you can only prove that all the integers that you know of, none of them are the largest integer, or not just the ones you know of, but all the integers period, none of them are the largest, well then that also implies that there must not be a largest. So let's see if we can take it one step further. So we go one step further, we're going to flip this one on the inside again. Okay, so now what's this one saying? This one's saying all integers are such that, so for any integer n you want, there exists some other integer m, such that n is not greater than or equal to m. So pick any integer, I get to pick the integer n, I'll pick one. Now you get the chance to pick an m. Can you pick one so that my integer is not bigger than yours? Yeah, just pick my integer plus 1. There you go, you win. Okay. So this one's saying, what this one's more saying is that for any integer, you can find an integer that is not greater than or equal to it. Now that last bit has kind of a double negation in it that again, our internal logical computers doesn't like. We don't like double negations. It confuses us. We usually like to eliminate them. So I'm going to move that in one more time. And here's where we need to apply a little bit of mathematical reasoning. What does it mean when we take not and apply it to greater than equal to? Well, not greater than equal to means less than. So I'm going to flip that sign around when I bring the not in. Now let's see if we can rephrase that last one. All integers are such that there exists an integer that is bigger than them. So this is for, or I'll say another way, for any integer n, there exists an integer m that is bigger than it. Or let's try and, again, take away the logic keys, try and turn this just into a more natural language sentence. It's saying every integer has a bigger integer. Or, Qui-Gon Jinn, there is always a bigger fish. So this is just saying there's always a bigger integer than the one that you can pick. So pick any one you want, there's always a bigger one. Okay? And that's, of course, logically equivalent to saying there is no largest integer. Okay? There is no largest integer is logically equivalent to saying for all integers, there must be a bigger integer. Pick any integer you want, there must be a bigger one. Okay? Now, these are logically equivalent. Now, sometimes we're going to prefer this final version. And the reason we prefer the final version is it looks a little simplified. It's got that negation out of there. It's more of a positive assertion than the negative one. This one's saying there isn't something. This one is saying something about what there is. What there is for any integer, there's one that's bigger. In fact, for any integer, there are infinite that are bigger, which is sort of cool too. Okay, but all of this comes out of this. So again, here we're just playing or working with logical quantifiers and seeing what happens when we negate them. And in this case, this was just a fun example as we sort of translate from one logically equivalent sentence to another. We see that each one expresses it expresses something different in the sense that the words we use to express the proposition are different. But these logical equivalency signs are saying that they're all the same. They're actually expressing the same thing, just with a different set of words, a different expression. Okay, interesting and cool. All right, so I think we've probably hashed this out enough, but this is saying for every integer there exists an integer that is greater. That was the final one, which is logically equivalent to there is no largest integer, which is where we started. Okay, that's, again, a cool little example. Okay, so what happens now when you have multiple types, or multiple quantifiers? We saw an example there already with 2, and we started flipping them around and doing stuff, okay? But here, what I'm going to express here is that when you have for alls or for exists, and they're in the same order, or not in the same order, they're consecutive, that's what I mean here. If they're consecutive to one another, then we can just lump them together. It doesn't matter what order they are in. So saying for all x and for all y, p, x, and y is the same as saying for all y and for all x, p, x, and y. So we usually just lump them together, something like this. Okay. Same thing for exists x, exists y. It doesn't matter what order we put them in, so we'll usually just lump them together. However, that is not true when we have nested quantifiers of different types, so we can't just flip them around. Okay, this is not necessarily true. It might be true every once in a while, but it's not necessarily true for any arbitrary propositions that you might be working with. Okay, so let's take a look at this one. This one says, well, I don't know. My brain has forgotten what we were working with on the other slide. It might mean the same as this. So let's see if we can work with this. This says there exists an n, an integer. Okay, there's some integer such that for all integers, n is less than m. There exists an integer such that for all integers, n is less than m. That's saying, okay, so let me say it one more time. There exists an n such that for all m, n is less than m. That's saying there's a smallest integer. That's not right. That's not true. But remember when we flip these two around, if we had the for all first and the exists after, we were saying that for any integer there's always a bigger one. And that was true. So actually flipping these two around took a true statement and turned it into a false one, and again vice versa. So that is an example of a case where we definitely don't want to mix up the order of our quantifiers. Okay. Now, like I said, every once in a while you might come up with a proposition where flipping them around actually does preserve its truth value, but if you find a proposition like that, that is a special case. That is an interesting case. Most of the time it's not going to be that way, so don't mess up the order of your quantifiers. Okay. All right, I think I've come to the end of this video where I was just trying to introduce these quantifiers and some of the cool, interesting properties related to them. But we are going to now apply these quantifiers or use these quantifiers in some of the definitions related to algorithm analysis. And so that's where I want to pick up in the next video. So thanks again for watching this video, and we'll see you in that next video.